Okay, so today we're going to be covering converting to binary. We're going to be starting off here with base 10, but before we do that, we just want to go back to our basic number system. Obviously, we use base 10 nearly every day, and most people think binary is a little confusing. There's really not all that much to it. Uh, Looking at how we create our numbers, this is our 10 to the zeros place or our ones place. It's our 10 to our first place or our tens place. And this is our 10 to the second or our 100ths place. This is true in binary as well. Just do this over here. 2, 3, 4. Okay, so this is our to the zeroth place or our ones place, to the first or our twos place, to the second or our fours place, and finally to our third or our eighths, our eight place. So just keep that in mind as we move forward. So we're going to start. The easiest way I've found to convert our values to binary is to take our value in base 10. And since it's binary base 2, we're going to divide by 2. We're going to save these values in a quotient in our remainder column. So 172 divided by 2 would be 86 with our remainder of 0. 86 divided by 2 would be 43, remainder of 0. 43 divided by 2 would be 21, remainder of 1. Okay, so now that that's complete, we're going to look at our remainder column here. So this is our binary representation, and it's actually going to go from bottom to top as opposed to top to bottom. So 172 base 10 in binary be 10101100 base 2. All right, so let's double check this. We're going to use the same formula we applied here, just down here, and we're going to extend it out. So this is our ones place, it's our twos place, our fours place, eight place, 16 place, 32, 64, 128. Now, we only want to look at the values that have our ones in them because that's just 0 times 64 to like 0 times 64, so it's just 0. So we'll just highlight these values real quick. So we'll have 128 plus 32 plus 8 plus 4, which if we just do a running total real quick, 168 and then 172, we get back to 172 base 10, which if we check is exactly what we started with. Okay, moving on to octal or base 8. We'll just move that down here so we have some room. Okay, so there's two ways to do this. One involves converting to base 10 first. I find that to be the longer way, and that typically causes more mistakes. So I'll just show it real quick. We're going to use the same exact formula that we just applied to convert it back to base 10. So do 2 times 8 to the second plus 5 times 8 to the first plus 4 times 8 to the 0. So we get 60 would be 128. That would be 40. And that would be 4, which would be 172 base 10. And then from there, we'd have to go through this process again, and eventually we get that output. However, that takes a little extra time. Like I said, it's more math, which will likely lead to more errors. Now, the easiest way to do this is octal, as we can see up here, only takes 3 bits to hold. So to do this, we can look and just do that real quick. This is our ones place, this is our twos place, and this is our fours place. So since this is a 2, this binary representation would simply be 0, 1, 0. Our 5 would be 1, 0, 1, and our fourth place would be 1, 0, 0. So the other thing, really quickly, if you don't know, basically octal only has values 0 through 7, which is why we can actually use this. Essentially, the highest value you can get with 3 bits would be 4 plus 2 plus 1, which is 7, and the lowest you could get is 0 because it'd be all zeros. Alrighty, so now looking at this, 0, 1, 0, 1, 0, 1, 1, 0, 0. And this is our base 2. This is our binary. All the steps it took was simply just converting each individual value to its binary equivalent and then concatenating them. So, as we can see, our values are essentially the same. There's just this leading 0 that really doesn't affect it at all because this doesn't affect the fact that 073 is equal to 73. So yeah. All right. We'll quickly look at our hexadecimal or base 16. So where things get a little bit more confusing for some people. So base 16 means we have values 0 through 15. Now, once we hit 9, we decide to go to A. So our A value, it'd be 10. And then from there, B is 11, C is 12, D is 13, E is 14, and finally F is 15. So looking at this, our A is going to be 10, and our C is going to be 12. All right. Since it is now hex as opposed to octal, it's going to be actually 4 bits of data to store these values. So again, we're just going to do the same formula here. So this is our ones place, twos place, fours place, and eight place. So now we're going to try to make these values. So 10 is going to be 1 in our 8, 0 in our 4, 1 in our 2, and a 0 in our 1s. And then 12 is going to be 1 in our 8s, 1 in our 4, 0 in our 2, 0 in our 1s. All right, so then that actually is the binary representation for that. And we know this because it's the same as these values that we have up here and right here. And just to double check that it is actually 172, we're going to do essentially the same thing we did right here. And we're going to do A, which is 10. And we're going to do C, which is 12. We're going to do 10 times 16 to the first, and we're going to do 10 times 16 is 0, and we're just going to add those values. Oh, whoops, that's going to be 12, actually. My apologies. So 160 plus 12 equals 172 base 10. All right, so there's one other important thing to note. Once again, you could have just done the step to begin with and then converted it to binary like we did in the first step. I strongly again suggest against that. The more math you do, the more likely you are to do a mistake. This really isn't all that much math over here. Other than that, I'll go ahead and zoom on out if you guys want to take a quick look, pause the screen. I hope you guys enjoyed the video. Have a good one.